The Permian Extinction. Anatomy of the Great Dying. Introduction to the catastrophe. Planet Earth has existed for approximately 4.5 billion years. Throughout this immense stretches of deep time, the biosphere has suffered 5 major mass extinction events, moments when the diversity of life crashed, and the course of evolution was irrevocably altered. Of these 5, one stands apart in its severity and its apocalyptic completeness. It is known formally as the Permian-Triassic extinction event, but among paleontologists and geologists, it is frequently referred to by a darker name, the Great Dying. Occurring approximately 251.9 million years ago, this event represents the closest life on Earth has ever come to being completely extinguished. It was a moment when the planetary life support systems collapsed so thoroughly that roughly 96% of all marine species and 70% of terrestrial vertebrate species vanished. It was the only known mass extinction of insects. The event ended the Paleozoic era, the era of ancient life, and ushered in the Mesozoic, the age of dinosaurs. To understand the magnitude of this event, one must look beyond simple statistics and examine the intricate web of life that was dismantled and the geological violence that caused it. The story of the Permian extinction is a detective story played out across millions of years of rock strata, involving volcanic eruptions of incomprehensible scale, oceans turning to acid, and a sky that turned lethal. It is a narrative of destruction, but also of the resilience that allowed the surviving fraction of life to rebuild the world we know today. The world before the end. To understand what was lost, we must first reconstruct the world of the late Permian. It was a planet vastly different from the one we inhabit today, both in its geography and its biological inhabitants. By the late Permian, the continental drift that drives the motion of Earth's tectonic plates had smashed the world's land masses together to form a single supercontinent known as Pangaea. This colossal landmass stretched from pole to pole, shaped roughly like a giant sea, cradling the Tethys Ocean to the east. Surrounding this island Earth was the vast global superocean, Panthalassa. The formation of Pangaea had profound effects on the global climate. With so much land concentrated in one mass, the moderating influence of the ocean was lost for the continental interior. The center of Pangaea was a place of extreme continentality, characterized by arid deserts, scorching summers, and freezing winters. It was a harsh environment, yet life had adapted remarkably well. The flora of the Permian was dominated by gymnosperms, seed-producing plants that had evolved to withstand drier conditions than their spore-producing ancestors. The southern portion of Pangaea, known as Gondwana, was covered in vast forests of the seed fern, Glossopteris. These trees were deciduous, shedding their tongue-shaped leaves seasonally, creating thick mats of peat that would eventually become the massive coal deposits of the southern hemisphere. In the northern regions, conifers and other drought-resistant plants thrived. This vegetation supported a complex ecosystem of terrestrial animals. The dominant land animals of the Permian were not dinosaurs, which had not yet evolved, nor were they mammals, though the ancestors of mammals were ruling the land. These were the synapsids, often described as mammal-like reptiles, though stem mammals is a more accurate term. The synapsids were diverse and successful. They ranged from small, insect-eating burrowers to massive herbivores like moss chops, a barrel-chested creature with a thickened skull. The apex predators of this world were the gorgonopsids. These were terrifying animals, possessing a mix of reptilian and mammalian traits. They had long snouts, saber teeth similar to later cats, and a sprawling yet somewhat upright gait that allowed for bursts of speed. The largest gorgonopsids, such as Innostrancevia, grew to the size of large bears and hunted the slow-moving herbivores of the Pangaean plains. Alongside the synapsids were the sauropsids, the lineage that would eventually lead to reptiles, dinosaurs, and birds. In the Permian, they were generally smaller and less dominant than the synapsids, occupying niches as small lizard-like insectivores or semi-aquatic herbivores like the parasaurs. The parasaurs were heavily armored, cow-sized reptiles that roamed the landscape in herds, relying on their bulk and bony osteoderms for protection. The marine realm of the Permian. While the land was teeming with strange proto-mammalian life, the oceans of the late Permian were home to some of the most diverse ecosystems Earth had ever seen. The warm, shallow waters of the Tethys Ocean and the continental shelves surrounding Pangaea were constructed of massive reef systems. However, these reefs were not built by the scleractinian corals we know today. Instead, they were formed by a consortium of sponges, calcareous algae, and distinct orders of rugose and tabulate corals. These reefs provided a habitat for a kaleidoscope of marine life. Brachiopods, shelled animals that superficially resemble clams but belong to a different phylum, were the dominant bottom dwellers, carpeting the seafloor in billions. Crinoids, or sea lilies, created underwater forests, their feathery arms filtering food from the currents. Ammonoids, shelled cephalopods related to squid and nautiluses, swam through the water column, diverse and abundant. The Permian Ocean was also the final stronghold of the trilobites. These armored arthropods had ruled the seas for hundreds of millions of years, surviving previous extinction events. By the Permian, their diversity had dwindled, but they were still a present and iconic part of the marine fauna. Sharks of bizarre shapes patrolled these waters, including the helicoprion, famous for its tooth-whorled jaw that resembled a buzzsaw. The marine food web was complex and seemingly stable, built upon a foundation of plankton and supported by efficient nutrient cycling. There was little indication in the fossil record that this thriving biosphere was sitting on the precipice of oblivion. The transition from the vitality of the Permian reefs to the dead zones of the early Triassic is one of the most abrupt shifts in geological history. The Siberian traps. The primary engine of the Permian extinction was not an asteroid from space, but a geological catastrophe originating from deep within the Earth. In the region we now call Siberia, a mantle plume, a massive upwelling of superheated rock from near the Earth's core, began to rise toward the crust. As this plume reached the lithosphere, it triggered a volcanic event of distinct magnitude. These were not standard volcanic eruptions like Mount St. Helens or Vesuvius, which are localized and explosive. This was a flood basalt event. The crust fractured, and fissures opened up across thousands of kilometers, spewing fountains of liquid basaltic lava. This event created the Siberian traps, a large igneous province that eventually covered an area of roughly 7 million square kilometers, roughly the size of the continental United States. The volume of lava extruded was staggering, estimated at up to 4 million cubic kilometers. However, it was not the lava itself that killed the world. A localized lava flow, even one the size of a continent, would not cause a global mass extinction on its own. The true danger lay in the specific geology of the Siberian basin. As the magma rose toward the surface, it intruded into a sedimentary basin rich in coal, petroleum, and evaporites. The heat from the magma baked these carbon-rich sediments, essentially turning the Earth's crust into a colossal fossil fuel refinery. This contact metamorphism released massive quantities of greenhouse gases. Carbon dioxide and methane, liberated from the cooked coal and organic shales, blasted into the atmosphere. Simultaneously, the heating of evaporate rocks rich in salts released vast amounts of sulfur, chlorine, and fluorine. This process transformed the Siberian traps from a regional geological event into a global climate weapon. The eruption phases lasted for hundreds of thousands of years, pulsating with varying intensity. The dating of these rocks, using high-precision uranium-led geochronology on zircon crystals, has revealed that the main pulse of the eruptions coincides perfectly with the extinction horizon found in sedimentary rocks around the world. The smoking gun is chemically fingerprinted in the rock record. The carbon isotope ratios found in rocks from the time show a massive spike in light carbon-12, a signature of biological carbon being released into the atmosphere. This confirms that the source of the carbon was organic, the burning of the coal and petroleum deposits of Siberia. Global warming and hypercapnia. The injection of trillions of tons of carbon dioxide and methane into the atmosphere triggered a rapid and extreme episode of global warming. Estimates suggest that global temperatures rose by 8 to 10 degrees Celsius. This is a catastrophic increase. In the interior of Pangaea, already hot and arid, temperatures soared to levels that were physiologically lethal for most multicellular life. The metabolic machinery of plants and animals has thermal limits. Proteins denature and cellular processes fail when temperatures remain consistently too high. The tropics became a dead zone, so hot that almost nothing could survive, forcing mobile species to migrate toward the poles, which themselves had become temperate to warm. However, the heat was only the beginning. The rise in atmospheric carbon dioxide led to hypercapnia, an excess of CO2 in the blood. For land animals, this would have caused respiratory acidosis, a condition where the blood becomes too acidic, disrupting the function of enzymes and the central nervous system. Animals with active metabolisms and high oxygen requirements would have been hit hardest. This may explain why the active gorgonopsids perished, while some of the burrowing, slow metabolism synapsids like Lystrosaurus managed to survive. The air itself was becoming toxic. The massive release of sulfur aerosols initially caused short-term cooling and acid rain, stripping the land of vegetation, before the long-term warming of the CO2 took over. The acid rain would have devastated plant life, further collapsing the terrestrial food webs, ocean acidification, and anoxia. While the land was baking, the oceans were undergoing a chemistry experiment gone wrong. The vast amounts of carbon dioxide in the atmosphere dissolved into the ocean, forming carbonic acid. This process, known as ocean acidification, lowered the pH of the seawater. For organisms that build shells or skeletons out of calcium carbonate, such as corals, brachiopods, mollusks, and some plankton, this was a death sentence. In acidic waters, it becomes metabolically expensive or strictly impossible to precipitate calcium carbonate. Their shells would have thinned, dissolved, or failed to form during larval stages. The total collapse of the Permian reef systems is a direct testament to this acidification crisis. The reefs vanished, not to return for millions of years. Compounding the acidification was the problem of anoxia. As the planet warmed, the temperature difference between the poles and the equator diminished. This reduced the strength of global ocean currents, which are driven by temperature gradients. Ocean circulation slowed down, and the mixing of oxygen-rich surface waters with the deep ocean ceased. The oceans became stratified and stagnant. Oxygen levels plummeted, creating vast, dead zones that expanded from the deep ocean onto the continental shelves where most marine life resided. This widespread anoxia suffocated organisms that required oxygen. Into this oxygen-starved environment stepped a new killer. In the absence of oxygen, anaerobic bacteria thrive. Specifically, biological markers in the sediment suggest a bloom of green sulfur bacteria. These microbes use sulfur for photosynthesis instead of water and release hydrogen sulfide gas as a byproduct. Hydrogen sulfide is highly toxic to most aerobic life. It smells like rotten eggs and interferes with cellular respiration. The Permian oceans effectively became a toxic soup. The presence of isorenuretine, a biomarker for these specific bacteria, indicates that the hydrogen sulfide-rich waters rose into the shallow photic zone. Models suggest that this toxic gas could have been released from the ocean surface into the atmosphere, poisoning land plants and animals, and depleting the ozone layer. The breakdown of the ozone layer would have exposed the remaining life to sterilizing ultraviolet radiation from the sun, causing mutations and reproductive failure in pollen and spores. Fossilized pollen from this era often shows deformities, supporting the theory of intense UV stress, the collapse of the terrestrial ecosystem. On land, the devastation was total. The forests of Glossopteris that covered Gondwana disappeared. They were replaced by fungi. In the geological record, right at the extinction boundary, there is a phenomenon known as the, quote, fungal spike. It is a layer of rock containing an abundance of fungal spores and very little pollen from trees. This signifies a world where the trees had died and were rotting, providing a massive feast for the decomposers. The breakdown of the forest ecosystem led to extreme soil erosion. Without tree roots to hold the soil together, the rich topsoil was stripped away by the acid rains, dumping massive amounts of sediment into the oceans, which further choked the marine ecosystems. The animal life of the Permian was decimated. The large herbivores, the parasaurs and the decinodonts vanished. The carnivorous gorgonopsids, the top predators of the age, were wiped out completely. The extinction was not instantaneous, but likely occurred in pulses over tens of thousands of years, tracking the pulses of magmatism in Siberia. Each pulse of gas release would hammer the ecosystem, preventing recovery. Those species that survived the initial heat might have succumbed to the acid rain, or the starvation that followed the plant die-off, or the hydrogen sulfide poisoning. It was a cascade of catastrophes. The insects, usually the ultimate survivors, suffered their greatest loss in history. Several orders of insects, including the Paleodictyoptera, large insects with piercing, sucking mouthparts, went extinct. The silence on the continents would have been profound. The lush, noisy forests of the Permian were replaced by barren, eroding landscapes populated by a few hardy disaster taxa. The marine extinction event. In the oceans, the loss was catastrophic. The trilobites, having survived for nearly 300 million years, finally met their end. Not a single species survived into the Triassic. The eurypterids, or sea scorpions, also vanished. The rugose and tabulate corals were wiped out, extinguishing genetic lineages that had built reefs for eons. The brachiopods lost over 90% of their genera. The intricate food webs of the Paleozoic were dismantled. The ocean floor, once teeming with bioturbating animals that churned the sediment, became laminated and undisturbed, a sign that the burrowing worms and clams were gone. These dead layers in the rock record are stark evidence of the suffocation of the seas. The only survivors in the oceans were those organisms that could tolerate low oxygen, high acidity, and high temperatures. These were often small, thin-shelled, generalist feeders. The Lilliput effect is observed in the aftermath, where surviving species are significantly smaller than their pre-extinction ancestors. Being small provides a survival advantage in resource-poor and stressed environments. The early Triassic, a broken world. The period immediately following the extinction, the early Triassic, was a time of extreme environmental instability. It is often described as a, quote, post-apocalyptic world. For nearly 5 to 10 million years after the extinction event, the Earth remained in a state of flux. The carbon cycle was broken, swinging wildly. Temperatures remained lethally high. This period is characterized by the coal gap, For millions of years, no coal deposits were formed anywhere on Earth. This indicates that forests had not yet recovered. There was simply not enough peat accumulating to form coal. The land was dominated by scrubby lycopods and ferns, plants that could grow quickly and reproduce by spores. The fauna of the early Triassic was dominated by a single genus of synapsid, Lystrosaurus. Lystrosaurus was a pig-sized, herbivorous burrower with a beak and 2 tusks. It was not a particularly impressive animal to look at, but it was a master survivor. It had a barrel chest that may have accommodated large lungs for breathing in oxygen-poor air, and its burrowing lifestyle offered protection from the extreme surface heat. At one point in the early Triassic, Lystrosaurus accounted for nearly 95% of all terrestrial vertebrates. It is unprecedented in Earth's history for a single genus to dominate the planet so completely. It was a disaster taxon, thriving in the empty world where competitors and predators had been swept away. The oceans of the early Triassic were equally bleak. They were dominated by microbial mats, similar to the stromatolites of the deep Precambrian past. With the grazing animals gone, slime took over the seabed. The recovery of marine life was agonizingly slow. It took millions of years for complex reef systems to return. When they finally did, they were built by a new group of organisms, the scleractinian corals, the ancestors of modern reefs. The ammonoids, which had been nearly wiped out, recovered relatively quickly, radiating into new forms, but they would face repeated smaller extinction pulses throughout the Triassic. The rise of the archosaurs. The Permian Extinction cleared the ecological board. The dominant lineages of the Paleozoic were gone or marginalized. This vacuum created an opportunity for a previously minor group of reptiles to rise, the archosaurs. In the Triassic, the archosaurs rapidly diversified. They evolved better water retention strategies than the synapsids, excreting uric acid paste instead of urine, which saved water, a crucial adaptation in the hot, arid post-extinction world. They also developed more efficient respiratory systems. From this archosaur lineage emerged the crocodiles, the pterosaurs, and eventually, the dinosaurs. The synapsids, the ancestors of mammals, were relegated to the shadows. They became small, nocturnal, and insectivorous. While the archosaurs grew massive and conquered the day, the synapsid survivors spent the next 150 million years under the feet of giants. However, this period of suppression was crucial. It forced the synapsid line to evolve traits like endothermy, warm-bloodedness, acute hearing, and perhaps lactation and fur to survive in the niches the dinosaurs ignored. In a way, the Permian extinction set the stage for the eventual rise of mammals, but only after a very long detour through the age of dinosaurs. Geological evidence and scientific consensus. The deciphering of the Permian extinction is a triumph of modern geology. For decades, the cause was debated. Some favored a bolide impact, similar to the one that killed the dinosaurs. However, no convincing impact crater of the right age and size has ever been found. The bed-out structure off the coast of Australia was proposed, but largely rejected by the scientific community due to lack of definitive shock quartz or iridium layers. The evidence overwhelmingly points to the Siberian traps. Geologists trace the layers of ash and basalt. They measure the mercury spikes in the rock record, which serve as a proxy for massive volcanism. They analyze the boron isotopes in ancient shells to reconstruct the pH of the oceans. They look at the stomatal density of fossil leaves. Plants grow fewer breathing pores, stomata, when CO2 is high, and the fossil leaves from the Permian-Triassic boundary show a drastic reduction in stomata, confirming the spike in carbon dioxide. The alignment of the extinction timeline with the eruption of the Siberian traps is now considered one of the most robust correlations in Earth science. Comparisons to the Anthropocene. The study of the Permian extinction is not merely an academic exercise in ancient history. It holds a chilling relevance to the modern world. The mechanisms that killed the world 252 million years ago, rapid injection of greenhouse gases, global warming, ocean acidification, and anoxia, are the exact same mechanisms occurring today due to human activity. While the source of the carbon is different, volcanic burning of coal versus human burning of coal, the atmospheric result is identical. Scientists compare the rate of carbon release during the Permian event to the current rate of anthropogenic emissions. Disturbingly, current estimates suggest that humans are releasing carbon dioxide into the atmosphere at a rate that is faster than the peak emissions of the Siberian traps. The Permian release took place over thousands of years, while the modern pulse is occurring over mere centuries. The total amount of carbon released in the Permian was likely higher than our current reserves, but the rate of change is the critical factor. Ecosystems cannot adapt to rapid shifts. The ocean acidification we are observing today, leading to the bleaching of coral reefs, is a direct echo of the chemistry that dissolved the Permian reefs. The expansion of hypoxic dead zones in our oceans today mirrors the onset of the Permian anoxia. The Permian extinction serves as a worst-case scenario for climate change. It defines the upper limits of the biosphere's breaking point. It shows us that the Earth system is not infinitely resilient. There are tipping points, thresholds, beyond which positive feedback loops take over. In the Permian, once the methane hydrates, frozen methane in the seabed, began to melt due to the initial volcanic warming, they released even more greenhouse gas, causing further warming in a runaway cycle. This runaway greenhouse effect turned Earth into a dying planet. Understanding the Great Dying provides the most powerful argument available for the urgent management of global carbon emissions. The legacy of the Great Dying. The Permian extinction was a bottleneck for all life on Earth. Every human, every dinosaur, every flower, and every bird that has existed since is a descendant of the few survivors of that cataclysm. We are the offspring of the disaster taxa. The genetic diversity of the planet was pruned back to a bare minimum. It took nearly 10 million years for the planet to recover its biological complexity, and nearly 100 million years for the biodiversity to return to pre-extinction levels. The event fundamentally restructured the biosphere. The Paleozoic dominance of fixed, filter-feeding marine life was replaced by the Mesozoic dominance of mobile, active predators. On land, the synapsid dominance was broken, allowing the archosaurs to claim the world. It illustrates the role of contingency in evolution. Survival in a mass extinction is not about being the fittest in the Darwinian sense of being the best adapted to the normal environment. It is about having the luck of possessing traits that happen to be useful in a hellscape. The Lystrosaurus was not a superior animal to the Gorgonopsid. It just happened to live in a burrow and eat anything. The Permian extinction remains a stark reminder of the power of geological forces and the fragility of life. It is a testament to the intricate connections between the solid Earth, the atmosphere, the oceans, and the biosphere. When one component changes drastically, the others follow suit with devastating consequences. As we look at the red strata of the Permian-Triassic boundary, we are looking at a scar on the face of the planet, a reminder of the time when life almost ended, and a warning for the future we are currently shaping. Deep dive into the geochemistry. To truly grasp the mechanics of the Great Dying, one must delve deeper into the geochemistry of the crisis. The carbon isotope excursion mentioned earlier is the primary tool. Carbon exists in two stable isotopes, carbon-12 light and carbon-13 heavy. Photosynthetic life prefers carbon-12 because it is energetically easier to bond. Therefore, living things and the fossil fuels derived from them are enriched in carbon-12. When the Siberian traps cooked the coal basins, They released this light carbon back into the atmosphere. This shifted the global ratio of carbon isotopes in the atmosphere and oceans. When we analyze limestone rocks from the extinction boundary, we see a sharp negative excursion in carbon-13, meaning the ratio of heavy carbon dropped because the environment was flooded with light carbon. This excursion is global, found in rocks from China to Greenland, confirming the global nature of the carbon injection. Furthermore, calcium isotopes tell the story of acidification. The fractionation of calcium isotopes changes depending on the saturation state of the ocean. The data indicates a massive dissolution event. This wasn't just a slight drop in pH, it was a collapse of the carbonate saturation state, making it chemically impossible for aragonite, a form of calcium carbonate, to exist in solid form in the upper ocean. This explains the selective extinction of organisms with heavy calcium carbonate skeletons, while organisms with silica or phosphatic shells fared slightly better. The role of methane hydrates. While the Siberian traps were the trigger, many scientists believe a secondary amplifier was necessary to reach the scale of the Permian catastrophe. This is the clathrate gun hypothesis. Methane hydrates, or clathrates, are crystal lattices of ice that trap methane molecules. They exist in vast quantities on the continental slopes of the oceans, kept stable by cold temperatures and high pressure. As the volcanic CO2 warmed the atmosphere and subsequently the oceans, these thermal pulses eventually reached the seabed. If the water warmed enough to destabilize the clathrates, massive bursts of methane would have been released. Methane is a greenhouse gas roughly 25 to 80 times more potent than carbon dioxide over short time scales. A sudden release of oceanic methane would have caused a hyperthermal spike, pushing temperatures beyond the point of no return. Carbon isotope patterns in some high-resolution sections suggest multiple pulses of light carbon, which is consistent with the volatile release of unstable methane reservoirs. The physiological filter. Recent research has focused on the physiological kill mechanism. This approach models the metabolic needs of Permian animals against the changing atmosphere. The combination of high heat and low oxygen, hypoxia, is deadly. As temperature rises, an ectothermic, cold-blooded animal's metabolism increases, meaning it needs more oxygen. But in the Permian, oxygen levels were dropping, and the heat reduced the oxygen solubility in water. This created a metabolic squeeze. The animals needed more oxygen than ever before, right at the moment when it was least available. This squeeze would have compressed habitable zones. Marine animals would have been forced into higher latitudes. Cooler water holds more oxygen, and shallower depths. However, the shallow depths were the most prone to overheating and UV radiation. There was literally nowhere to hide. This physiological modeling explains the size reduction in survivors. Smaller bodies have lower absolute oxygen requirements and better surface area to volume ratios for gas exchange. The plant crisis and river systems. The crisis in the plant world fundamentally altered the physical geography of the continents. In the Permian, rivers were largely meandering. The roots of plants stabilized riverbanks, creating narrow, deep channels that snaked across the floodplains. When the plants died off, this stabilization was lost. The geological record shows a shift from meandering rivers to braided river systems. Braided rivers are wide, shallow, and chaotic, consisting of multiple channels separated by temporary sediment bars. This shift indicates a landscape where water flashed across the surface, carrying massive loads of loose sediment. This sediment surge would have buried potential habitats and smothered freshwater ecosystems. It took millions of years for the meandering river style to return, marking the slow recovery of riparian vegetation. The recovery of the insects. The recovery of insects is a fascinating subplot. The Permian extinction wiped out the Paleodictyoptera. but it also opened the door for the modernization of the insect fauna. In the Triassic, we see the rise of the hollow-metabolous insects, those that undergo complete metamorphosis: egg, larva, pupa, adult. This strategy might have been advantageous in a recovering world. The larvae and adults often occupy different ecological niches, e.g., a caterpillar eats leaves, a butterfly drinks nectar, preventing competition between generations. This separation allowed these lineages to exploit the recovering ecosystems more efficiently. The ancestors of modern beetles, flies, and bees began to diversify in the shadow of the Great Dying. The superanoxic ocean. The term superanoxic has been used to describe the ocean state. It wasn't just the bottom waters. The anoxia shoaled into the water column. Biomarkers for green sulfur bacteria have been found in rocks that were deposited in shallow, sunlit waters. This means the toxic, oxygen-free water rose all the way to the photic zone. This is terrifying to contemplate. A purple-colored, stagnant ocean, smelling of rotten eggs, releasing poisonous gas clouds that drifted over the coastal lowlands. It explains why the extinction was so severe in the shallow shelf seas, which are usually the most resilient parts of the ocean. The kill zone was everywhere. The geographic disparity. While the extinction was global, it did not affect every region identically. The high latitudes, near the poles, seem to have served as refugia for some species, though even there the losses were heavy. The tropical regions were the hardest hit. In the early Triassic, there is a quotorial gap in the fossil record. For millions of years, the equator was essentially devoid of vertebrate life. It was simply too hot. Temperatures in the tropics may have exceeded 40 degrees Celsius, 104 Fahrenheit, in the ocean, and even higher on land. Complex life fled the equator, leaving it to the bacteria. This latitudinal gradient of extinction intensity helps scientists map the progression of the warming. Evolutionary bottlenecks and genetic drift. The extreme reduction in population sizes during the extinction event led to significant genetic drift. When a population crashes to a few individuals, the genetic variation is largely lost. The survivors rebuild the population from a tiny genetic toolkit. This is known as the founder effect. The Triassic recovery fauna shows signs of this. Many species appear morphologically uniform. The explosion of diversity in the later Triassic and Jurassic comes from the gradual accumulation of new mutations over millions of years. The Permian Extinction essentially reset the evolutionary clock, forcing life to innovate from scratch. This is why the Triassic is such a strange period, filled with experiments in evolution, gliding lizards, monkey-like reptiles, and bizarre armored marine forms, many of which did not survive to the Jurassic. Nature was throwing spaghetti at the wall to see what stuck in the New World Order. The future of research. Research into the Permian extinction is ongoing and intense. New techniques are constantly being applied. High-resolution magnetostratigraphy helps align rock layers across continents. CAID TIMS. Chemical abrasion isotope dilution. Thermal ionization mass spectrometry allows for dating of zircon crystals with error margins of less than 50,000 years, providing incredible temporal resolution. Geologists are currently scouring regions in South China, which has some of the best preserved marine rocks from the boundary, to reconstruct the timeline of the pulses. There is also a focus on the terrestrial record in the Karoo Basin of South Africa, which provides the best unbroken sequence of land animal fossils. The goal is to link the marine and terrestrial extinctions precisely. Did they happen at the exact same time? Or was there a lag? Current data suggests they were nearly synchronous, reinforcing the atmosphere-driven kill mechanism. The end of an era. Conclusion. The Permian extinction stands as the ultimate cautionary tale of planetary history. It demonstrates that the Earth is a single, interconnected system. A geological event in Siberia can kill a trilobite in the ocean on the other side of the world. The atmosphere is the integrating vessel. By changing the chemistry of the sky, the Siberian traps changed the chemistry of the ocean and the temperature of the land. Life, despite its resilience, has limits. When the rate of environmental change exceeds the rate of evolutionary adaptation, extinction is the result. The Great Dying was not just a bad day for life. It was a near-death experience for the biosphere. The fact that we are here today to study it is a miracle of survival. As we navigate our own era of environmental turbulence, the lessons of the Permian about carbon, heat, and the fragility of ecosystems are more relevant than ever. The ghosts of the Gorgonopsids and the trilobites speak to us from the rock record, silent witnesses, to the time when the Earth burned. We would be wise to listen to their story. The closure of the Paleozoic era was absolute. The world that emerged in the Triassic was fundamentally different. The dominant plants changed from the great seed ferns to the conifers and cycads. The dominant animals shifted from the heavy, sprawling synapsids to the agile, erect-walking archosaurs. The dominant marine life shifted from the stationary filter feeders to the mobile hunters. The Permian extinction did not just kill species, it killed a way of life. It destroyed the Paleozoic evolutionary fauna and replaced it with the modern evolutionary fauna. The structure of marine ecosystems today, dominated by clams, snails, crustaceans, and bony fish, is a direct result of who survived the Permian bottleneck. In a very real sense, the modern world was born in the ashes of the Permian catastrophe. The deep time perspective offers a humbling view of our place in history. We often view the Earth as a stable background for human history. The Permian extinction reminds us that the Earth is dynamic and capable of violence on a scale we can scarcely imagine. The Siberian Traps eruptions were a natural event, a roll of the geological dice. Yet they unleashed forces that nearly sterilized the planet. Today, humanity has become a geological force in its own right. We are moving carbon from the lithosphere to the atmosphere at rates comparable to the traps. The study of the Permian is the study of our own potential future if we fail to manage the planetary thermostat. It is the darkest chapter in Earth's history, but also one of the most educational. It teaches us the value of the stable climate we inherited and the terrible cost of losing it. The Great Dying is not just history. It is a warning written in stone. Detailed look at the synapsid survivors. Among the few survivors, the therocephalians are worth noting. These were advanced synapsids, close relatives of the cynodonts, the direct ancestors of mammals. Some therocephalians survived the extinction, likely due to their small size and perhaps burrowing habits. During the early Triassic recovery, they briefly flourished before eventually declining. However, the most important survivors were the cynodonts. These small, unassuming creatures possessed the traits that would define the mammalian lineage: differentiated teeth, secondary palates, allowing them to eat and breathe at the same time, and likely higher metabolic rates. They passed through the fire of the Permian extinction and the arid wasteland of the Triassic to eventually give rise to the first true mammals in the late Triassic or early Jurassic. We are here because these small, scrappy synapsids refused to die. Their survival is the thread that connects us to the deep past. The role of volcanogenic mercury. A relatively new proxy in studying mass extinctions is mercury. Mercury is released in large quantities during volcanic eruptions. Unlike carbon, which cycles through the biosphere, mercury is a heavy metal that settles out and remains in the sediment. High concentrations of mercury have been found in Permian-Triassic boundary rocks globally. This provides a physical link between the sedimentary record of extinction and the igneous record of the Siberian traps. The spikes in mercury correlate with the spikes in extinction intensity. This helps rule out other causes. An asteroid impact would not leave a sustained multi-pulse mercury signal over hundreds of thousands of years. The mercury data serves as a fingerprint of the culprit, confirming the volcanic hypothesis beyond reasonable doubt. Ozone depletion mechanisms. The mechanism for ozone depletion involves the release of halogens. The Siberian traps magma intruded into salt deposits, evaporites, rich in organohalogens. The heat volatilized these compounds, sending methyl chloride and methyl bromide into the stratosphere. These are potent ozone-destroying chemicals. The collapse of the ozone layer explains the prevalence of mutated pollen grains found in the fossil record at the boundary. Without ozone, UVB radiation bombards the surface. This causes DNA damage. For plants, this damages the reproductive machinery. For animals, it causes cataracts, skin damage, and immune system suppression. The combination of a hot, toxic, and UV-irradiated world created a perfect storm of stress factors. It is difficult to imagine a more hostile environment for life. The recovery of the reefs. The reef gap lasted for nearly 8 million years. Reefs are the rainforests of the ocean. They support massive biodiversity. Their absence in the early Triassic fossil record is stark. When reefs finally returned in the Middle Triassic, they were small and patchy. It wasn't until the late Triassic that large, complex reef systems re-established themselves. This long recovery interval suggests that the environmental conditions remained hostile long after the initial eruption ceased. The ocean chemistry had to stabilize, the temperature had to drop, and the acidification had to be neutralized by the weathering of rocks, a process that consumes CO2. This lag time represents the, quote, planetary hangover from the binge of volcanic gases. The Triassic takeover. The void left by the extinction allowed for the rise of the dinosaur morphs. In the mid-Triassic, small bipedal archosaurs began to appear. They were fast, agile, and efficient. Because the established ecological incumbents were gone, these early dinosaur relatives faced little competition. They rapidly diversified into the three main lineages of dinosaurs: the theropods, meat-eaters, the sauropodomorphs, long-necked herbivores, and the ornithischians, beaked herbivores. By the end of the Triassic, dinosaurs had become the dominant large land animals, a position they would hold for 160 million years. The Permian Extinction cleared the stage for the Dinosauria. Without the Great Dying, the large synapsids might have retained their dominance, and the age of dinosaurs might never have happened. Evolution is a series of sliding doors. The Permian Extinction was the biggest one of all. Final thoughts on the Great Dying. The Permian Extinction is a complex puzzle that scientists are still piecing together. It involves geology, chemistry, biology, and atmospheric science. It requires us to imagine a world that is alien yet oddly familiar. It is a story of how the Earth can turn on its inhabitants, but it is also a story of life's tenacity. Life did not disappear. It hunkered down, adapted, and eventually flourished again, filling the empty world with new forms and new songs. The Great Dying was the end of the ancient world, but it was the beginning of the modern one. As we study these ancient strata, we are learning about the resilience of the biosphere and the fragility of the climate system. It is a history lesson we cannot afford to ignore. The rocks remember.